Hey everyone, welcome to the lecture for 5.2 on series. So we just finished up a sequence. So just to be extra clear, a sequence is a list of numbers. So let's say we start at 1 and go to infinity. So this is just A1, A2, A3, A4, etc. A series is going to be a sum, an infinite sum. So it's the same kind of structure with the A representing the term and then the index given by n. But instead of just listing them out, we're going to add them up. So now the idea is to consider this infinite sum as a limit of sorts. So obviously none of us have time to sit around and add an infinite list of things together. So the method is to create a partial sum. So notice here in the top part of the definition, we have just what the infinite series is. In the middle part, we're going to define a partial sum. So instead of going from 1 to infinity, we're going to stop at some arbitrary value k. So now this is a finite sum. And adding a finite number of terms is very doable. To go from a finite sum into an infinite sum, we just want to take the limit as k goes to infinity. So the idea is that we go from the partial sum here. Sorry, it should be n. So you want to go to the infinite series. And so hopefully it's clear that the way to do that is just evaluate the limit as k goes to infinity. So the limit as k goes to infinity of sk equals the limit as k goes to infinity of the partial sum from n equals 1 to k of a sub n. And so this is our infinite series. So let's do some examples. Again, the idea here is going to be to determine what the partial sum structure looks like, and then to take the limit of that. So I'm going to do C first, and then we'll head back to B. And I skipped A, but you're welcome to read it in the text. So if I have this sum here, then I want to take S1. So this is just the partial sum that has only one term in it. So this is 1 over 1 times 2, so just 1/2. And then I'm going to just do a few of these to see if I can determine the structure of the partial sum sk. And the other thing I want to start doing too is I'm just going to simplify them at the end. So this will bring me to 2/3. So then S3 and so you could do this for as many as you need to determine the structure of the partial sum. But for me, I'm kind of already, and I've already worked this example, but for me, I'm already noticing that this has a nice little form. Namely, it's just k over k plus 1. So if I want to evaluate the sum, the infinite series, all I have to do is take the limit as k goes to infinity of sk, which is the limit as k goes to infinity of k over k plus 1, which is just 1. So this is why it's really important to get an expression for s sub k, because if we don't have that, it'll be very hard to take the limit. For b, it's a bit of a different story. So the first, if I'm only looking at the first term, I'm just going to get -1. And the second term is -1 plus 1, which is 0. And the third term -1 plus 1 minus 1 equals -1. So this is just oscillating back and forth between -1 and 0. So we can see that it's not going to approach anything. So the limit as k goes to infinity of sk does not exist. Possibly the most important series that we're going to learn about in this class is going to be the harmonic series. So it's just the sum of 1 over n, so 1 plus a half plus a third plus a fourth plus et cetera and so on. And so there are so many awesome proofs of why this diverges, and there's a million ways to skin this cat. They're all fun. For now, we just need to know that it diverges. So store that in your notes. You're going to need to know that for the rest of the entire chapter. Okay, algebraic properties. It's basically kind of works the same way that an integral does. You can split it over sums and you can pull out scalar multiples. So that's all we're saying, is that if we have a sum or a difference, we can split it up into 2 summations. And if we have a scalar multiple in front of our term, then we can pull that out. So let's see if we can use some of these algebraic properties to determine the value of this summation here. So the first thing I want to do is I want to break it up into 2 pieces. So here we just use the first property. And then I'm going to go ahead and pull out this 3 as well. And the reason I'm doing that is because this looks really similar to the first example that we did. And if I pull out the 3, then it's identical. So 1 over n times n plus 1. And then I'm going to do something sneaky over here. So notice that it's n minus 2. So we definitely could just work with this, but I want to show you, I guess I would just call it like a maneuver. So we have n equals 1 to infinity of 1/2 times n minus 2. So this actually equals n equals 1 to infinity of 1/2 to the -2 times 1/2 to the n. Right, so that's n minus 2. So if I pull out that 1/2 to the -2, that just becomes 4. And then the next thing I want to do is just look at this guy over here. So I'm going to use partial sums to determine what this is. You've probably seen this before. It's a very, very popular series called the geometric series. So S1, I'm not going to do all the, I'm not going to write everything out, but S1 is 1/2. S2 is 2/3. S3 is 3/4. No, it's not. That's a lie. Sorry. This is going terribly wrong. 1/2, 3/4, 7/8. And in general, SK is 2 to the n minus 1 over 2 to the k minus 1 over 2 to the k. So as a sum, I'm just going to take the limit as k goes to infinity of 2 to the k minus 1 over 2 to the k, and that just equals 1. So coming back down to the main problem, I get that this is just 4 times 1. And don't worry, we'll do lots more geometric series. And we saw earlier that the summation of 1 over n times n plus 1, that was just 1. So this equals 3 times 1 plus 4 times 1, and that is 7. So let's talk about the geometric series. We just saw an example where we had 1/2 to the n. So a geometric series is just where you're taking powers of some ratio r. Notice here that they start their summation at 1. So this is the cool thing that you can always do. So you don't have to start your summation at any particular point. Like I prefer to start my geometric series at 0. So there's, well, let's see. Right, so this would give me a times r to the n. So you could write this, if you don't like that form, you could write it that way. Another thing that you could do this is just showing a manipulation of how to work with series. But another cool thing that you can always do is in general, and this is like maybe one of my favorite, I don't know, series tricks to do. If you have a series, let's say n equals whatever, we can start. Actually, we can start anywhere. Let's just call it n equals n naught. And let's say we have a to the n. If I want to make my series start like 1 below, the idea is that I can drop the summation notation down by 1, but then I have to bring my inside up by 1. So this would be, if I bring it down here by 1, then that means in here I have to bring it up by 1. Right, so you're kind of just compensating in the indices. So for me, I use that to say, if I drop n by 1, that means I'll be at 0. But because I moved it down by 1, I have to add 1 back to the inside. So you may also see the geometric series in this form. And the reason why this is important is we have a formula to determine the value of a geometric series. So we were able to determine when it converges, and moreover, we know the value to which it converges. So if the ratio is less than 1, R, then this thing will converge. If it's bigger or equal to 1, then it'll diverge. So think about that. If you had like 2, so you're adding 2, then 4, then 8, then 16, and you're adding all that together, that thing's gonna blow up. So of course it's not going to converge. So you need to make sure that it gets small. And you may be wondering, well, the harmonic series, those terms get small, right? 1 over n, that gets small and small and small. And the thing about the harmonic series versus the geometric is that the harmonic series doesn't get small fast enough. So I'm going to scroll back up to the harmonic series really quickly just to write. So even though 1 over n, this guy goes to 0. That's not 0. Even though 1 over n goes to 0 as n goes to infinity, it doesn't go to 0 fast enough for the series to converge. In the geometric series, we see that the terms also will go to 0, but they're going to 0 fast enough and this thing will converge. So this is a super important formula to know. So let's go ahead and use it here in example 5.9. The key to using geometric series and using that a over 1 minus r is that you have to manipulate it into being of the correct form. So for a, looking at our formula, we either want it to start at 0. You can use either of these two forms. You either want it to start at 0 or you want it to start at 1. I propose let's have it start at 1, since first of all, the example already starts at 1, and second of all, equation 5.7 is already in the form. So I want it to start at 1, and I have that, so that's good. But the issue I'm having is that -3 to the n plus 1 doesn't fit with what I have in equation 5.7. So I'm going to do that sneaky thing where I just peel off copies. So I have n equals 1 to infinity, 4 to the n minus 1 on the bottom. I really need a -3 to the n minus 1 up here, which means that I need to pull off 2 copies of -3. So I have -3 squared. So if I add the exponents, it'll bring me back to n plus 1. That's my check to make sure I did this correctly. -3 is obviously 9. So now I'm going to pull that scalar multiple, and I have 9 times n equals 1. Actually, maybe even more fitting, I'll leave the 9 in there, but not in the fraction. So now we have 9 times -3 to the n minus 1 over 4 to the n minus 1. And I can, since both of these are being raised to the same power, I can go ahead and combine them as a single term. So I get n equals 1 to infinity of 9 times -3 over 4 to the n minus 1. And so now I look exactly like the form. N equals 1, I've got my a, I've got my r, and my exponents in the right spot. So using that, I'm going to have 9, which was a, over 1 minus r, which was -3/4. So simplifying this, I get 36 over 7. The one thing I didn't state outwardly was that r is less than 1. And that's really important, because just because you can use the formula doesn't mean that it's going to converge. You have to check the value of R being less than 1. So for B is going to be really similar. I'm going to go ahead and rewrite e to the 2n as e squared to the n. Right, so it's all about just reworking your summand. By the way, the inside of a radical is called a radicand. The inside of an integral is called an integrand. The inside of a summation is called a summand. So no surprise there. This is e squared to the n. But I really need this to be n minus 1, right? I need this to be something so if I just multiply it by an e squared, then putting those together will bring me right back to e to the n, so I'm good here. Our R value for this example is e squared, which is greater than or equal to 1, which means that this diverges. Okay, another super fun problem to do is writing a repeating decimal as a fraction of integers. So this may seem kind of out of left field, but it fits in nicely with the geometric series in the following way. So 3.26 repeating is 3 plus 26 over 100 plus 26 over 10,000 plus 26 over 1 million, plus et cetera, and so on. And so we can actually write this as 3 plus 26 over 10 squared, right? But now this is a sum to the n, right? So 100 and then times 100 times 100, then 100 times 100 times 100. So for here, n is starting at 1 and going to infinity. But the issue again is that we don't have n minus 1. So we still need to continue to rework this summation. So I'm going to write the 26 out in front just to give myself some more space. So I have 26 times, I really need this to be n minus 1. So in order to make these two things equivalent, I need to multiply by 10 squared, right? So if I added these exponents together, I would be back at n. Okay. Quick reorganization. So this 26 and this tail end 1 over 10 squared is 26 over 100. Then I have 1 over 10 squared to the n minus 1, and I'm going from 1 to infinity. So now I'm in the perfect form to use my geometric series. So this is going to be 3 plus 26 over 100 times 1 over 1 minus 1 over 10 squared, which, boy, that sounds awful. So 1 minus 1 over 100 is just 99 over 100. So I get 3 plus 26 over 100 times 1 over 99 over 100. So these fractions actually cancel and you'll end up with 26 over 99. So 3 plus 26 over 99. And if you write this as a ratio of two integers, then what you'll get is 323 over 99. Right, and so you need the geometric series to be able to pull out that closed form for the summation. Okay, last on our list of things to do today is to go over the telescoping series. So telescoping series, I mean, I think everything's interesting in this class, so I feel like maybe that doesn't pack as much of a punch, but I claim that it's still very interesting. It's just a cool thing that happens. I mean, think of an actual telescope, like it all just collapses in on itself. So A telescoping series is one where it all collapses in on itself except for a few terms. So you'll have a lot of cancellation. For example, when we had the summation 1 over n times n plus 1, actually, let's really go full out. You guys just finished your partial fraction decomposition, so this should be a breeze for you. So consider the example that we had before, where we had 1 to infinity of 1 over n times n plus 1. I want to write this as the sum of two different fractions. So let's use a PFD. 1 over n times n plus 1. We can go about this the same way. We have two distinct linear factors. So this is going to be a over n plus b over n plus 1. So then I'll get 1 equals a by n plus 1 plus b by n. And so now instead of a killer x, we have a killer n. So if n equals 0, then 1 equals a. And if n equals -1, then -1 equals b. So what I can do, just like we wrote it before using the integration, except now we're in a summation, this is going to be n equals 1 to infinity of a over n, which is just 1 over n, plus b over n plus 1. So that's -1 over n plus 1. Okay, so the return of partial fraction decomposition. So now let's look at SK. So SK is just the partial sum so I get 1 over 1 minus 1 over 2 plus 1 over 2 minus 1 over 3 plus 1 over 3 minus 1 over 4. And what are we noticing right off the bat? We kind of have this bookend situation where these 1/2 cancel, et cetera, and so on. So what's going to happen here is that we're going to get, on the end, 1 over k minus 1 minus 1 over k plus 1 over k minus 1 over k plus 1. And all this stuff cancels. So the halves cancel, the thirds cancel, the quarters cancel. Everything up to the k's is all going to cancel out. And what we're left with, which is why it's called a telescoping series, is 1 minus 1 over k plus 1. So if I wanted to compute the summation, it's just the limit as k goes to infinity of 1 minus 1 over k plus 1. I can't think of an easier limit. So that's telescoping series. And if you ever look at maybe you have like a polynomial in your summand, you might want to think about whether or not it becomes telescoping, and always keep partial fraction decomposition ready in case you need to break it apart. All right, so let's look, this one's pretty straightforward. So last example, we're going to evaluate this telescoping series. So SK equals, n equals, SK is the summation from n equals 1 to k of cosine of 1 over n minus cosine of 1 over n plus 1. And so this is just going to equal cosine of 1 over 1 minus cosine of 1 over 2 plus cosine of 1 over 2 minus cosine of 1 over 3. So this is really the same thing that happened last time, plus cosine of 1 over 3 minus cosine of 1 over 4, et cetera, and so on, until we get to the kth term, where we're going to have cosine of 1 over k minus cosine of 1 over k plus 1. And so again, we have all these cancellations all the way up until k. So what we're left with is cosine of 1 minus cosine of 1 over k plus 1. And to determine the value of this summation, we're going to do n equals 1 to infinity. Just kidding. We're going to take the limit as k goes to infinity of sk. And that just is going to turn this last part into cosine of 0. So cosine 1 minus cosine 0. Cosine of 0 being 1. So this is cosine of 1 minus 1. P.S. cosine of 1 is not 1. That's like a really common kind of like little brain fart mistake I see often. So that takes care of series. Good luck, and email me with any questions.